Good afternoon, everyone. My name is Joxean, and I'm going to talk about how I researched a bit doing machine learning, applying machine learning techniques to reverse engineering, and how I apply them to a tool that I write myself, which is called Diaphora for doing binary diffing. So, machine learning, artificial intelligence, whatever it is called, seems to be a hot topic in the academia for binary code similarity analysis, or as we call in the industry, diffing, binary diffing. In this talk, I will try to discuss how a machine learning engine was added to Diaphora, which is a program diffing tool that I write myself, and the problems that I found during the path doing that. This is basically what I'm going to explain. First, the why I wanted to do so. Then talk about the prior knowledge that I found on these fields. Then talk about the three main ideas, which were train a local model, train a big, gigantic, huge, as you want to say, model, or train highly specialized models, and then my own very own conclusions about this stuff. So first of all, a disclaimer, I'm not a machine learning guy at all. I'm a reverse engineer, only that. And this is how I basically started learning about this stuff. The basic idea of this research project was to say, OK, Diaphora finds a lot of matches and can do binary diffing between different binaries for the different architectures, and different platforms, whatever. But there is room for improvement. How can I improve it? Perhaps can I use machine learning or something like this to improve somehow it? So let me summarize very, very, very briefly what is binary diffing. When we are talking about binary diffing for two binaries, it is basically a process of two parts. Mapping, where we find matches of functions, two functions, function A in binary 1, function B in binary 2, which are the same function in both binaries. Okay? This is the process of mapping. And then the other part is classification. Once we have a match, we need to determine if the match is good, is reliable or not, if it is bad. And optionally, at least in Diaphora, for example, I calculate a similarity ratio. How close both functions they look one to the other. Okay? OK, so how can I use machine learning techniques, whatever they are, in order to improve any of these steps that binary diffing is actually can be summarized as in? To be honest, I have no idea how to leverage any kinds of machine learning techniques in a way that scales for doing binary diffing, but for finding matches, for classifying them, is actually what is supposed that machine learning is very good at, right? Writing classifiers. So, OK, this is what I started doing. Fine, this is the idea that it has, and the next thing that you have to do is check what is the prior knowledge on these fields, and then try to go from there. So in the reverse engineering industry, basically all of us use either Diaphora or bindiff or gitdiff for doing binary analysis for our works. Okay? But none of these tools, the standard industry standard tools, apply machine learning techniques until today. So there is nothing I can learn from the industry, right? Next, go to the academia, where I'm sorry, but I don't usually like it too much in this field. So almost every single paper that I have read lately about binary diffing coming from the academia tries to apply machine learning techniques, generative artificial intelligence, somehow to these fields. Some of the most popular tools are bindiff, alphadiff, or bindiff neural network. Anyone here knows any of those tools? Crickets? So I'm not going even to ask if you use them, because usually it is even more crickets. So the problem, at least in my cases, I read a huge number of papers that try to leverage machine learning, artificial intelligence to binary diffing, and it was either fairy tales, or there was nothing useful, or it was terribly classical. Like one of the papers actually uses bytes to try to do binary diffing for a reason that I still do not understand. Or they simply use assembly. probably this is my opinion, but I found nothing even remotely useful. So next step, think about how to do so. So this is the list of ideas that I had before actually writing any kind of code, or better said, the two first, OK? Train a local model, train a gigantic model. And the third idea that came along the way was maybe training specialized models. I will go with more details about it later. So the first idea, training a local model. On my mind, this was awesome. On my mind, it was like, OK, Diaphora used a number of heuristics to find matches, OK? And then the initial matches that Diaphora finds are highly reliable. OK, maybe I can use the highly reliable matches to train a local model by building a data set from then telling, OK, these are very good matches. And then I build some bad matches. And I tell this model, OK, these are good matches, these are bad matches. Now, do magic, learn, and then give me back a model that I can use to verify that the next ones, that the next matches that I'm going to find that are not so reliable, that classifier can tell me if it looks like it's reliable or not. What do you think? This idea looks like it'll work or not? Worst idea ever, or at least during my testing. So basically what I implemented, it was in the code in Diaphora in the public GitHub for months. Then I dropped, nobody used, nobody even commented anything about it anywhere. And during my testing, it was a bad idea. How it works is Diaphora finds reliable matches. Then we train a classifier using these matches. And then we use Diaphora to classify future new matches, and use the classifier we trained based on Diaphora's classifier to determine if the results are good. Do you see the problem? The problem is that I was trying to learn a model that I already coded. What's the point? No point. And also, due to generalization of the results, I'm going to add some false positives on top. So probably you don't want to do that. Don't waste your time, as I did. So the next step was, after I saw that this idea was not working, I said, OK, maybe it was obvious, but I didn't know until I applied this. So OK, the next thing, what is what most people do? Train with a lot of data. So on my mind, it was like, OK, I'm going to train a model with binaries, compilers with GCC, and with CLAN, and with Microsoft Visual C for Linux, Windows, Android, Mac, for Intel 86, ARM, MIPS, PowerPC, RISC-V. And it is a thing that just works, right? I build a huge data set, then I extract somehow the data and convert it, and then train a model, and it generates somehow a model that I can use as a classifier. What do you think about this idea? This works or it doesn't? Maybe. If you have resources that I don't, it will probably. So let's talk about why going from the beginning. Data sets. So the problem of building a big model, a huge model, trying to learn from a huge data set is building that huge data set, right? So the first thing that I did is try to search for data sets that already exist and that I could use for learning a model from this data set. There are not so many data sets out there, and the data sets that are out there, from all of them, I finally ended up trying to play with these two ones, and even these two ones are not good enough. So the first one that I want to mention is from the Johns Hopkins Applied Physics Laboratory dataset that was built by EVMSec. This, the Old Star, is a public repository of Debian sources, binaries, compiler artifacts, and what's not. And the other one is the Cisco Talos binary function similarity dataset, well, set of datasets. Actually, Josh, the first speaker today, mentioned us talked about this paper and this dataset. And, well, the first dataset that I mentioned, the one from the All-Star guys, is 1.1 terabytes. It contains around 32,000 Debian packages, 20,000 binary executables for Intel 86, AMD64, ARM, PowerPC, MIPS, and S390X, if you still use it. Which means that even if I use some, I don't know, 8 terabytes disk for storing all the data set and all the IDA databases, supposing that I can, in some time that makes sense for me, analyze everything, it will still be a lot of resources only for the initial step. Also, this data set is not good enough for me, because it has no binary for Windows, no binary for Android, no binary for iOS, Mac, nor RISC-V support, nor Microsoft Visual C. The other one, the Cisco Talos dataset that I mentioned, it is split into 3 different datasets. The one is called the dataset vulnerability. Then there is dataset 1 with that set of binaries, which is very big. And then we have dataset 2, which is smaller. And long story short, the only one that I could use myself and analyze in a time that made sense for me was dataset 2. So most of the talk, this talk, will be about how I use this dataset 2 at first. Okay? Still, this dataset, I mean, when it is manageable for me, I can use it. It's still a vast dataset, because it doesn't contain binaries for the different compilers. It is only for Linux. It has a limited number of architectures that it is built for. But anyway, now I have a dataset. Even when it is a small one, it's not a toy. It's something that makes sense. Next step, build from this raw data something that I can work with. So the dataset 2 is basically 4,047 binaries, executables, that I analyze with IDA, export with Diaphora, and it generates 4,047 SQLite databases. Obviously, you don't want to work with 4,000 databases, so I wanted to extract from the columns that Diaphora exports something smaller and something more manageable that I could have in a single place, in a single SQLite database or in a single CSV file, as I finally did. So long story short, from the so many fields that Diaphora exports, I decided to go for the ones that you see in the list that is called fields, which means basic blocks, adds, the in degree, the out degree, cyclomatic complexity, a very complex signature to explain using prime values as signets to different parts of the abstract syntax tree. Later I do a workshop. If you want an explanation, it will be better later, OK? And many other fields. Then I do a lot of comparisons between them and generate the fields that in this slide are called prime fields, OK? Basically, I take the smaller value, the biggest value for numeric values, and the difference between them, doing this calculation, like I mentioned here. And for textual representations, the pseudocode, the compiler, both the clean version and the version as the X-rays the compiler spits out, I just calculate the similarity ratio using sequence matcher quick ratio from Python. OK, still, after doing this, and building and having which fields I want, you still have 4,047 binaries that you want to compare against 4,046 binaries. Because you want to compare every single binary against every single binary to have the similarity ratio of them. It is roughly 16 million operations. I started writing the code for doing so. I make it highly optimized for running at home. And finally, when I was working at the maximum that I could optimize it, I make an estimation after 100 binaries, and it told me around 2 months. Fine, not for me. Perhaps for you, but not for me. So I needed a partial solution, something, because the best solution, building a huge data set, is not at all for me. So the other approaches that I thought about were building a subset of the data set that is significant enough. Significant enough is hard to measure. and hard to define and hard to get. Or building specialized data sets for very specialized use cases, which is a different idea. Or building a data set comparing only binaries that match around some percent, 99% of the addresses of the functions, or 99% of the function names. In case these binaries have function names, they have symbols. And well, this is another idea that I started playing with. So I started playing first with the idea of trying to find the perfect subset that will work for everyone. So only working with diffutils, only working with Koret, only working with the set of binaries from Putin, from different LS versions. Guess what happened? No surprise here, right? No one subset was working properly for other subsets, for other data sets. So this is an example with the data set from diffutils. I built a model. The model with the training data, it has the usual accuracy, precision, recall F1 acceptable, very good, 0.9. And then when trying to use that model for other data sets, the values are very different. Like, for example, with a biggest testing set from the wall dataset 2, which is called the dataset CSV file here, we can see that both the precision, the recall, and the F1 are bad, not as good as before. Other examples with the PuTTY binaries, 0.9 values against itself, the training data, no surprise, but then you have to extrapolate and use it against something else. Using the same testing data set, the values were very bad. Even 0.4, did not work for us, for me. Against the diffutils data set, the same. And after doing it for a lot of times, I decided that it wasn't working. I didn't know what, and I thought, maybe it is the algorithm. No, it is not the algorithm, but I have to test it anyway. So I started testing many different algorithms just to see if I get some different results. In the table that you have here, I'm highlighting the final algorithm that I'm using is a simple decision tree classifier, which is very easy to interpret, very easy to build. And basically, taking a look at the data, to the accuracy on the training data that you don't really care, and then trying to apply it to your model, to whatever data set you are using for testing, I did not find a huge difference, except on the time for executing it. Some algorithms are really slow, like taking hours, not only for training, but even for predictions, for some reason with the model I built. So I discarded them. These are other tests as I did, the same that you will see that there are not huge difference when you are using a different algorithm or not here. This is a bit more accurate data in case you want to lose your time taking a look here. Finally, I decided that the decision tree classifier was fast enough and accurate enough for what I wanted. I did not want to make Diaphora even more slower. So this classifier was good enough. I don't really mind about overfitting for now, because I don't have the resource to train a huge model anyway, so I don't mind. And this is it. The random forest classifier solves work, or actually works better during my testing. It's slightly better, but it takes far longer, both doing training and both using it as a classifier later. So I decided to discard it. And then getting back, after discussing the problems I had with big data sets and briefly discussing that algorithms aren't the solution or the problem, to be honest here, what else can I do? Does this testing mean that I cannot, as an independent reverse engineering tool developer, train a model I can distribute? Maybe not. Or maybe not a gigantic model. Does this mean that I cannot use it? No, because actually I'm using it finally. So training specialized models. The third idea is not an idea that I had before. This idea appeared after I started trying to build a gigantic model, and I realized that I did not have the matching required for that, the disk required for that. So basically, what I thought is train a model with 2 or more binaries with and without symbols that are actually the same target. but for different versions, maybe, and then try to use that model to try to improve function matching for future later versions. What I mean, well, I will explain it a bit later. What do you think about this idea? This works or doesn't? This was the first idea that I got working. This is an example, an abstract example. Let's say that we have some version of some software that we started reverse engineering at version 1.0. They forgot to strip the symbols. So we open IDA with the binary without symbols. We strip them. And the same binary, but with the symbols. Then we perform the cross comparison with the tools that I distribute now with Diaphora. We generate a CSV, we train a model, and then we use that model for future versions where they do not have any symbol at all to tell them, look, this classifier is trained over good matches that we know for a fact that they are very good from previous versions. Does this improve somehow importing functions and matching functions in future versions? So I needed a real use case, and what I use is MP Engine. MP Engine is the Microsoft antivirus engine, which is huge. And what they usually do is they publish the new MP Engine DLL version today, and symbols aren't published until 1 month later. And sometimes they even forget, or whatever, I don't mind, to publish the symbols. But you have previous versions. So I took the binaries 19700 and 20,000 with symbols and with no symbols. I built a data set, then I trained a model, and then I tested it. The model was built like this. What I know that are good matches, the same function, I generate them with a label that is 1, good, and then I generate some 5 random matches that are bad, so I have some balance of good and bad matches. And well, after all, it builds a decision forest for 300 megabytes with 1,600,000 rows on it that is so easy to watch, too easy to understand, that the model looks good to me. After doing a very brief testing with some very rudimentary integrations into Diaphora, it improves slightly the new matches from the new versions of MP Engine. So I said, OK, let's give it a try to this model. And for that reason, I didn't know what I expected. I tried to use this model to try to use this model for the Cisco Talos dataset 2 that I mentioned before. Naturally, the results were horrible. So now you cannot train a specific training model for a different set of binaries and then magically expect that it will work with a different set of binaries. Not at all. Yeah. Surprise. So after this step, that was kind of clear. And considering that I don't have the resources that I will need for building a gigantic model, and that smaller data sets don't really work with other different data sets, what can I do? What I thought is perhaps I can create a very specialized data set by taking all the binaries from the Diaphora testing suite, all the binaries from the dataset 2, and also all the binaries that people, since Diaphora is already 9 years old, OK? Every single binary that somebody reported to me trying to Diffing or having problem, issues, questions, or whatever, I made a model training over all of them. I cannot share these files because these ones are private, the other ones are totally public, and the results are pretty good, actually. So this is an example that later I realized that in a screen you are not going to read, but I can tell you. So this is a haiku loader for RIX5, trying to be Diffing against a haiku loader for Intel 8664. These are the matches before using the model. It says that there are 433 partial matches. Take a look at the 3 functions that are highlighted. This is without using the machine learning model. This is after using the model. The 3 highlighted functions are the same as before. But now we have a lot of other functions that are appeared, and the similarity ratios significantly improve. And now, instead of 433, we have 501 results in this specific case. So the dataset I built using the Diaphora testing suite binaries and all the binaries in dataset 2 is what I call the amalgamation, which is a dataset that is available there in that URL. The dataset is not huge. Using B and zip2-9, I managed to make it 50 megabytes compressed, so you can download. I can upload to GitHub because it has limitations. Let's talk about it a bit. So after building the amalgamation model, I did some manual tests in Diaphora to see how it was performing with other tests. Overall, what I found is that it was finding more partial results, more results that were not obvious at first. And after testing some of them, because one thing is that it is finding more matches, and another thing is if these matches are good or not. If I'm adding false positives, it doesn't work for anything, right? After taking a manual look to hundreds of results, it took out that it was not adding a number of false positives that is significant. And actually, because Diaphora has some internal mechanisms to try to get rid of false positives as much as possible. So the next step was to try to first revalidate the model by taking the dataset, the whole dataset, splitting it into the usual train, validation, and testing datasets, doing again all the tests that I did from the beginning. This is how I split, simply into 60% for training, 20% for testing, 20% for validation, randomly shuffling the dataset, the final dataset that I built. The results were actually very good at first, finally. And after the model over the data told me that the model was working as I wanted, and then I coded the code to support this classifier into Diaphora, and did testing a lot of tests with the whole Diaphora testing suite. The whole Diaphora testing suite with what I call the slow binaries, things that are huge kernels or binaries from things that are having like 300,000 factions. It takes a week, so I cannot show you all the results. But I can tell you about some of them. Like, for example, this one. This is VisiBox Intel 8664 with no symbols against VisiBox for PowerPC with symbols. Without machine learning techniques, it was finding 1,212 results. I know that you cannot read it properly. Trust me, then you will see it on the slides if you want. 1,212. After this, 1,301. Better results, not a lot, but it improves. More matches, more. This is a haiku loader for Intel 8664 with no symbols against the one from RISC-V with symbols without using the new machine learning engine. It was finding like 433 partial matches. Now it finds 488 partial matches with no false positives, proven going one per one to verify that there was none. This is the an old iOS kernel 10.3.1 against the macOS kernel 10.12.4. Without the machine learning engine, it was finding 4,134 functions, which is around 46% of the potential matches that it will find. After using the machine learning engine, it was finding now 4,927, which is 53.73% of the potential matches from both binaries. And after I did that, the problem is, I said that extrapolating data sets doesn't really work. The amalgamation works very well for me. But maybe for your project, because this binary is for something that I have not seen in 9 years, doesn't work for you. The natural thing is not for me just to distribute models already trained that maybe work, maybe don't. The thing is, I distribute the data set, I distribute the tools, and then you do it yourself if you need. So since now I'm distributing the model and the tools and the data sets, you have them in that URL. And basically, what you need to do yourself, if you want to build your own specialized model for your own project, is analyze all binaries with data, sorry, export all of them with Diaphora, run a tool that parses the SQLite database to generate a CSV file, use the generated CSV file to train a model, and then simply in Diaphora, edit the Diaphora config py file to tell which model you need to use. Naturally, you don't need to code all of this. This is an example script that actually works, that is already published, that does every single of the steps that I tell you. You simply need to put your binaries into a specific directory, change one file to put where is Diaphora installed, where is IDA installed, run it, and depending how big or how small it is, it will do all the work that you need. This is what you need to change in the Diaphora config.py, and that's about it. Now, let's suppose that you want to build your model, but you also want to use the model that Diaphora is supplying because it works for you, but you want to make it slightly specific for you, but also have all that it has. You can simply use the CSV file, the dataset that Diaphora is using for this model, decompress, concatenate the CSV from your model, then train over it, which is the Diaphora's amalgamation plus your data from your dataset, and then use that model that you build yourself, and that's about it. As simple as it sounds. And that's it. So my personal own conclusions about doing machine learning for real-world use cases in real-world reverse engineering tools. At least for me, it was not obvious at all at first sight which machine learning techniques might or might not work to apply to bin diffing, to be honest. And this talk has only covered using it for classification, not for mapping. Do you remember that at first I said that you can summarize the steps in binary diffing in mapping, then classification? Perhaps there are ways to apply it to mapping, but I know no way that works, that scales. Building huge models from huge data sets doesn't look appropriate for everybody. If you have big resources, that I don't, it might work for you. I don't have the resources, I cannot prove it. But still, even if it works, like for example in my case, even if I manage and somebody tells me, OK, here you have some huge machines, do the training and do whatever, perhaps then you need to distribute already trained models that are like 2 gigabytes in size or stuff like this, that I don't consider it very useful. But building highly specialized data sets and then training over them for your specific project, I have proved myself that it will work very well for you. So you are working on whatever version of whatever binary right now, and you already have a lot of reverse engineers. And then for the next version, it heavily changed, but it's still the same binary, it's still the same people working on it, it's still the same compiler. The model that you are trained over these binaries to try to improve matching for future versions is going to work very well. I proved it with MP Engine, which is not a toy project. I proved it with all the projects I cannot talk about. It's going to work. But in any case, more important than distributing a model or the data set that I publish are the tools for doing so, which I'm already distributing to. And that's it. So everything is public already. It is published there in GitHub. The binary diffing tool, Diaphora, already integrates that new model. It is only in the Git version. It's not, I haven't made a release version. Some people prefer to use release versions. I don't mind. And that's about it. Hopefully, it helps you in your reverse engineering projects. And after this, I have to run to do a workshop. So if you want to give it a try with your own binaries, your projects, or you have some more specific questions, you can make them on the workshop, or now if you want. Thank you. Any question?
model? How many function features you use for your model? The model you do.
How many functions per, sorry?
Features.
Features.
Yeah.
Oh, how many goals? Yeah. Give me a second. Not so many, to be honest. So the final set of features, you mean the columns that I use for the training for the data set?
In those CSV files.
Yeah, the ones that I put here in what I call the primed fields. I don't know how many there are, but I don't think they are like 30, less than it.
So there are control flow properties.
So there are control flow properties. There are pseudocodes, abstract syntax trees, some signatures that I better explain you later in more detail because they are huge. But yeah, graphs, I try to get rid of them because they generate a lot of false positives. The compilers generate an intermediate representation that is far much better. Some more questions? No? Thank you.